So the core thesis here of what we were going to start talking about is this idea of building minimal containers. But in true fashion, kind of speaking to myself, what we're really going to do is get extremely weird with containers right now. So for the folks who are not familiar with who I am, that's me. I'm Redbeard. Don't call me Brian Harrington. Just call me Redbeard. Harrington is, the name of a whole bunch of people who I don't identify with, so just keep it to Redbeard. It makes it real simple. And now, who here gets really excited about tarballs? Perfect. You're liars, but I'm glad to hear that because we're going to go exactly down the right path. So about 6-7 months ago, a colleague of mine named John Boole, who is the lead maintainer of Rocket, we were traveling across Europe, and when we were in Munich, we stopped in this coffee shop, and this book was just sitting on the table. And we were sitting there hanging out in Munich for an hour, just killing time before we go over to the actual space where we're giving our presentations. And that space in Munich was the first time that I gave this kind of minimal containers talk. So I've improved it a lot since then. There are now actually slides and actually things beyond just me hammering on a keyboard really loudly. But this kind of takes it back to where things all started. What we're going to do is talk about how all of this actually fits together and how it works. So first, let's break out the beer because it's story time. So there once was a little container who wanted to get to production. But much like Redbeard, he was getting a little bit too big in there. So all the production ops folks came in and said, if your containers are going to get deployed on my infrastructure, you better come correct on how big they are. Jed here was extremely psyched to have the big joke in there. He's an awesome guy. And then, to which the developers reply, but come on, disk space is so cheap. But SSD write cycles are expensive. And that's something to actually take away, because for a lot of different reasons, big containers are a problem. Big containers slow down your deployments, by the amount of time it takes them on the network. Big containers, they consume more disk space. They increase the cost of your object storage, affecting your budget. They decrease your I/O performance. They're harder to audit. Big containers need to be put on a diet. But you don't have to take my word for it. Let's actually look at an example here. So this is a piece of software that I pick on because I love it so much. Shout is effectively run your own IRC cloud. It's pretty great. I mean, it's a Node.js application that gives you this awesome web interface so that you have an IRC bouncer that stays online all the time because as open source, community members, just like me, you're on IRC 24/7. I have no doubt about that. You've got all your integrations hooked up so that when someone pings you in pound CoreOS, you get hailed on your phone and you can just respond immediately because you're that psychotic, just like me. But in reality, I like to pick on this partially because of how much I like the software, and because in the documentation for this piece of software, I pulled a screenshot. So they verify that the image has been created, and they have an 833 megabyte image for their IRC bouncer. Now, as I said, this is written in Node, so let's start breaking this apart. Let's open it up, decompose it, and get a better sense of what's actually happening here. So when we look at the source, it's 592 kilobytes. So let's do the math. 592, carry the 1, 833 megs. Okay, I missed something in there. Well, if we go back and look at the front page of their website, they say, hey, do an npm-g install shout. So clearly it's going to get some dependencies in there. Clearly it's going to be more than that 556K worth of source. It's going to compile some stuff. So let's look at their example of what the kind of canonical Docker file for creating this is. From Node, run that one command, expose, and shout start. It should always be as simple as that. That's probably what 2/3 of the Docker files in this room look like. They are find a sensible base, run commands to build the thing, expose port, specify what you need to do to actually do it. But you notice up there where it says from node. So we have to start decomposing this a bit further. I mean, this is where we have this wonderful, brilliant, perfectly red onion that we're about to slice for this taco. And we're about to start pulling it apart. So, we start looking and we get into, okay, well, they're doing apt-get updates and apt-get upgrades and install things. And, we make it a little bit more improved by going in and turning off all the interactive stuff. Oh, and then we want to do it secure, so we start adding in keys. And then we actually go back and look at the Node.js thing. And let's take a look at, this is the canonical Node Docker file. This is maintained by the folks at Joyent, who are the folks who curate Node.js. The idea being, if you can't trust them with something about Node.js, who can you trust, really? And they do a lot of even better things. They pull longer keys, they pull them directly from key servers to make sure that you get the right content. They identify them by ID. They do G verifications of all of the actual content. And that's it. But in the same way that we started with from node, and this is what node was, we get into from build pack deps, Jesse, and it just keeps going further and further and further. And if we just look at this Docker file, not the one that has our additional source in it, but we just look at that, we're still looking at 640 megabytes. 640 megabytes for an interpreter. What do we do about this? Seriously, what do we do? Well, we're going to demystify how a container is built. I've given you a little bit of preamble, I've hooked you in, now we're going to figure it out. Then we're going to enumerate other ways to do it, and then I'm going to show you how all of this works. I'm going to show you multiple different methods for actually getting this done. So let's step into the kitchen. And again, I ask, who gets excited about tar balls? So we're going to have a little bit of a mantra here. So do me a favor, repeat after Redbeard. A container file system is just a tarball. A container file system isn't magic. It's just a tarball. Okay, you've got it. If you have to walk out right now to go take care of the kids, wash your horse, do whatever it is you need to do, we're set. You've got that much and you can move on. But the idea is that anything that can make a tarball can do the heavy lifting to get a container into place. It's all that you need. So let's work through this. Step one, make a temporary directory. I think most folks can handle that. Even if you choose not to use maketemp, you can probably make a directory. If not, Linux Foundation has some wonderful training courses. I highly advocate everybody go through those. They're wonderful folks. But with comments, let's break this down a little further. So we're going to grab the Fedora GPG key. Curl, you can go verify it out of band. Using our temporary directory, we're going to import that key. RPM is the canonical tool that is used to actually manage a Fedora or Red Hat or CentOS or RPM-based system. So use the tools that distro expects. And then, in each of these, you notice that we specify a different root location for where these things are running. That is built into the tools. The tools are designed to do this. If you're not comfortable with an RPM-based distribution, use Dev Bootstrap. It's the same basic idea. You create a directory, you pivot to that directory, and then you use that as the base install location for all your content. Once that's done, you tar the directory up. We now have a tarball. Simple. What do you do with that hunk of junk? You import it. I assume, and we know what happens when you assume, I make an ass out of myself, but I assume that the majority of people here, when they say containers, they mean Docker. So I'm going to use Docker as some examples with this because, I want to be where you live on this. So you cat that stream into Docker import, There is actually a typo there. Fedora and the dash are transposed. It should be docker import dash space Fedora. But this is where the question comes up. Is it really that simple? Yeah. Really? Yes, it really is that simple. So let's break this down a little bit. So let's pull up a couple terminals here. I am gonna do the dance to figure out how to get both windows up at the same time. Or I'm just gonna do this. We're gonna exit out of that for a second. I'm gonna now have both my terminals, and now I can see everything that I am doing. Wonderful. So, first off, we're going to log into the host DO2. Running on DigitalOcean. Great. Hey, look, it's a CoreOS host, and there's no Docker images. And there's nothing there. Yet, I have this tarball that I created earlier, called fedora.tar. If I run and stream that into and give it a name, that last portion is just a name. All that it is doing, it is tagging the contents of that, and then as it progresses, it's streaming the data in, and when it's done, it will give me a raw container ID. This is in terms of Docker. So this means that I can actually just instantiate that direct container ID and get it done. So this was actually built using the commands that you saw before. I literally, because I knew it would work, went and ran the commands and then copied and pasted them back in, with the exception of the Docker import where I messed that up. But that means that I can say, Docker, run. I need a terminal. I'd like it to be interactive. Run that container, and give me the command bin bash. And look at that. I am inside of a terminal. And when I say cat etsy issue, I am staring at Fedora release 22. And when I control PQ out of that and do a docker ps, that container's running. There was no Docker file involved. It's an interesting point. You don't have to have a Docker file. Think of those times when you've done a Docker pull and you see getting image, getting image, getting image, getting image, getting image, and it turns into 40 layers deep. And that's because, well, developer A needed Vim enhanced rather than Vim in their container. Developer B, they needed ImageMagick, and ImageMagick needed libxml, and libxml needed some crazy kernel header because, and we'll get to that, but moving back to where we were at, we're going to talk about this a little bit further. Do you need a Docker file? Well, clearly no, you've seen that, but I'll humor you. If we wanted to do this same process now and throw a Docker file into it, keep in mind, I tagged that container ID as it was brought in. I tagged that file system image. So there we go. Now I have a Docker file. And let's play nice with this. So when I go in and say, well, actually, make dir Fedora, cd Fedora, vim Docker file, and I can even cheat a bit and say, from that long ID, if I can type correctly, and it uses that. And now I'm even one step further. I should have actually done that. So now I actually have a tag attached to my thing, and I can say docker run -t-i fedora v1.0, and it just lets me in. So if you need to specify these things like expose network ports and all the kind of default niceties that Docker provides you, give it environment variables and all that, you can do it. But we also get back to that idea of you are able to now know exactly what is inside that container. If I needed to go into this directory and just browse around a little bit, this is just a directory. If I want to embed my own content in it, that's now trivial for me to do. I go into, really, I know that none of you are actually doing things as root inside these containers. Wink, wink, nudge, nudge. I'm certain of it. But just since I'm a bad actor here, I'll change into this root directory, and if I need to put all the contents of my application in there, I can do that. And then again, when I tar this up, and when I run it through Docker import, it's going to be there. Everything's going to run fine. But there are some different issues with this that I think are interesting to talk through. So we're going to do that. So there are a lot of tools that we can use to do similar processes, as I mentioned. So when I did this, it was actually DNF, not Yum. You can also use Yum if it's a CentOS machine. DNF is the replacement for Yum that makes everything happy. You can use Deb Bootstrap if you prefer canonical slash Debian type distros. But you can also do Buildroot. You can use Alpine, and you can even directly use Gentoo. So keep in mind, for all of you power users who love building their own Gentoo distributions, Gentoo produces something called the Stage 3. And that is a tarball of a base Linux file system that is designed to make it easier to build your Linux distribution. Because Gentoo is not per se a Linux distribution. It's a meta distribution that's used as an SDK for building your own flavor of things. Wink, wink, nudge, nudge, guess what we use at CoreOS? But before we get into this, it's time for a PSA. Are you utilizing frame buffers, running window manager, administering users, logging in, editing files? Stop doing that in a container. That is what general purpose computing is for. That is not what a container is for. If you, on your security team, are arguing about PAM configurations inside your users' containers, you are messing things up. You do not understand the technology, and that's okay, because these are the early days on stuff, and everybody has to learn. But a container is not the place, per se, for a general purpose Linux distro. So now, I crack my knuckles and we go deeper into the inception. So, there is a wonderful tool called Buildroot. Buildroot is an SDK. You use it to build minimal Linux distros. When we say minimal Linux distros, we mean things like router distributions, like OpenWRT. All those folks that have, WRT54G, Linux-based Linksys routers that, you install new firmwares on. That's how they're built. They're built using Buildroot. And when you think about what you need in an embedded distribution on an embedded platform, do you need man pages? Mm-mm. Do you need Vim enhanced? No. It's nice to have Vim, but you don't even need that. So it starts getting into this game of what do you need? And Buildroot is so idiotically easy to use that I'm going to show you. On the fly, here we go. So I'm going to start by firing up Chrome. And this is going to be slightly awkward when I try to see into the window that I can't quite get to. But we do that, and then I go, okay, Chrome, go to buildroot.org. And when you get there, get the cursor to the right spot, they say, hey, here is our GPG key. Here is our newest release. So I'm going to grab that release. I'm going to get out of root, because you should never, ever, ever build things as root. Just for giggles, I'm going to make temp-d again, and now I'm going to go into temp S9. And now I'm going to download this. And as any good user of online materials would do, we're going to go through and actually verify the GPG signature. And it says, hey, that actually is a good signature for that file. I haven't personally trusted the key, but most importantly, it is a good signature. So since I trust the Buildroot website, good enough. So here we go. Actually, was that's. So I expand this, and I change into that directory. Step 1. If you've ever built a kernel before, you've probably run the command make menu config. This gives you a GUI for configuring your Linux distro. So we're able to go through and say, yeah, you know, let's make this specific to x86-64. And let's actually, as a part of our tool chain, yeah, we want the new kernel Linux headers, but do we want microlibc? No, we don't. I want glibc, because I live fast and wild, and I want every syscall available. None of this musel garbage for me. And I want the new version of glibc, and I want the new version of binutils, and I want the new version of GCC, and yeah, I want C++ support, because you need C++ support for IPv6. Things that I've learned by playing with all of this stuff. And no, I don't need a kernel, because I'm not building a full distro. And in fact, I don't need an init system at all. They were getting in their digs on systemd earlier, and I'll have my fisticuffs about that as a systemd appreciator. But at this point, I also have the ability to select packages, which makes sense. Now, this is, when they say packages, they're not saying packages like you think of deb files or RPMs. They mean they have a makefile system, and everything will be compiled from scratch. So I can go through here and say, yeah, how about you give me, do they have Nginx in here? Yeah, give me Nginx. So now I'm going to create a container with just Nginx. Or I can go back to my interpreted languages, and I can say, hey, give me the Node.js container. And on top of that, give me npm. So at this point, I save that, I exit out, and there's one more super complex step. I do that. Now this is going to take a little while, so I'm not actually going to make folks sit and watch through this, but you know, you'll notice here when we look back through this that they do this thing where they're downloading host gawk and they're downloading host GCC. That's because this doesn't expect you to have those pieces installed locally. This grabs them and manages its own dependencies. And if I wanted to add additional things to this, I can go into, which one was it? It was S9 build root. And I can go into my packages, and I can say, hey, yeah, let's do some stuff with 0MQ. And I want to actually look at how this is done. Now, 0MQ is a great example because what they do, they actually publish the hashes of the sources. So Buildroot will do the verification for you to make sure that things have not been messed with out of band. And then it has a makefile. And it is just a makefile. And on top of that, they have brilliant documentation. I wish that, okay, it's freaking out a little bit for me up here. I wish that the CoreOS documentation was a tenth of as good as this. It is astounding the amount of detail that they have going through everything about this, from building it to customizing it. So I have a lot of customizations that I have in my Buildroot configuration to make it super simple to build these minimal containers. Now, I have over here in one of these windows, back on this host, I'm going to exit out of that. We're going to get back into our regularly scheduled program. So I'm going to go in and I'm going to make a directory called shout. And first and foremost, I have corenode.tar. This is where I've already gone through in the past and built a build root container with Node.js and npm in it. So I'm going to say cat core node.tar into docker import from standard in and call it Node.js. Done. Now, part of the reason why that took so little time is because my Node.js container is 20 megs total. Joyance is 633 megs because they're relying on not compiling their own software from scratch. They're relying on compiling their software for a general purpose Linux distro and then bringing in everything that general purpose Linux distro says they need. Now, I want to take a time out here for a second, because a lot of folks are going, whoa, whoa, whoa. I didn't think that I was going to have to be compiling software to make my containers. And that's okay. Because in reality, this talk is probably not geared 100% at you. But what this talk does is it enables someone in this room to build the next Red Hat or Canonical of containers. It gives them the ability, that first push down the path in how they actually get to building a canonical resource of trusted containers that actually reflect the containerized world that we are all trying to get into. Because that's not reflected by just stuffing a general purpose Linux distro into a set of namespaces. It's not the case. So, time back in. I'm done with that rant for a second. So we've got this container imported. It's named Node.js. Now we're actually going to do something useful with it. So I go into shout, I do my vim Docker file, and I say from Node.js run npm -g install shout. I then go through and say command, if I can type at all, shout start, and then docker build -t shout that. Huh? Helps if I spell Docker file correctly. I run that command again. Now it immediately kicks off npm. And npm is going to do a lot of stuff because, in case you didn't know, much like Ruby, Node.js requires some compiling to actually happen in there. And there we see the output of npm, and it's done. And at this point, I realize, in true fashion, like anyone who builds a Docker file, I've forgotten something. I forgot my expose. Thank you. So I say expose 9000. I run this command again. And then I say docker run -p shout. And now that's listening on 9000. So what I'm going to do is I'm going to go grab the IP address of that by running my... The beautiful thing is that all these IP addresses will be destroyed by the time anyone watches this presentation. And so this is then where I have not actually exposed my configuration correctly. So let's do... Yeah, it did a random port, so actually let me do that in the background. And so I'm actually on port 32770. 32770. If I, okay, third time's the charm. And there we go. And shout's actually running. Now, we see that shout's running, but we missed one thing. 47 megs. 5% of the original developer's container size. And on top of that, I can tell you what I don't have in there. I don't have a lot of software that I don't trust, that I don't know where it came from, that I don't know what it's running, because I can actually go through the full logs of that build and know for sure what's going on. And that also means that my security team can now build that canonical container for me. They can verify that everything is as it should be, and fully rely on trusting the content that is there. So let's actually get back into all of this. So no, you don't need a Docker file. And yes, it is simple to do. And there are a lot of other tools that we can use to build that. And Buildroot is pretty simple to use. And the best part is that the tarballs that you're producing are just tarballs. They're agnostic. I showed you how to do this with Docker, but once you have that raw tarball, you can use that with systemd nspawn, you can use that with LXC, you can use that with Rocket. It really doesn't matter. The biggest thing that Docker has brought to the table is a wonderful mechanism for shipping tarballs around. I'm not saying that as a pejorative. I'm saying this as someone who is involved with getting the OpenVZ project off the ground, reporting SWSoft for a GPL violation. Whoops. I realized the pain very, very early on of what it took to actually build an OpenVZ container, and then later what it took to build an LXC container. And Docker has made this trivial. But it's time for the producers of software to finally catch up with what this underlying technology can do. And one of the most important things to me as a user gets into the idea of signing. Because now I can GPG sign my containers, I can GPG encrypt my containers, and I can have a much greater degree of control over who has access to these things, how they have access to them, and even more importantly, how they can be distributed. So at this point, I've been jabber-jawing for quite a while, and I'm going to switch it over to taking some questions. And now's the time for my standard. Chance, okay.
Do you know of any good tools that allow building Buildroot containers within, for example, other containers? Is there a Buildroot Docker
So
that has all those things?
So my earlier comment about Buildroot brings all of its dependencies is like a high school physics lie. It's a lie that I tell you to make it easier to understand all of this. And then when you get into college level physics, you unlearn all the lies that you learned in high school because they're very simple lies. Yes, all of this can actually be done in a container. I've done it as a proof of concept on CoreOS where you could kick off a job inside of Docker to do a Buildroot and produce an asset. Because the idea is that you would use a process through like Jenkins or through some container-aware CI system to make all of this stuff automated. So that now when there are security vulnerabilities that come out, you rebuild the pieces of your stack that need it. And you, for example, never have to worry about an SSHD vulnerability if you haven't put SSHD in your containers. And if you don't care about OpenSSL, regardless of whether or not Ubuntu thinks you need to care about OpenSSL, if you don't put that in your container, you are laughing all the way through the morning while you're making your cup of coffee when you go to work because everyone else is worried about OpenSSL and you're just kind of kicking back and chilling. So there's a lot of awesome things that can be done there. Okay, we have a question in the back, and then we'll come to...
Hi, thanks. So I'm going to reveal how very little I know about what you talked about. So my fairly informed understanding of Docker is that it is generally thought of as an application packaging and deployment technology.
Yes.
And what I heard you talk about in very vivid detail was not so much an application deployment technology, but in fact an operating system packaging and deployment technology, which is a little mind-bending, I'll be honest. And I was wondering, my question is, punchline, are people ready for that?
I think that increasingly people will become prepared for it because what this does is this now means that I make a choice about the Linux distribution that I want to run. And if a producer of software has produced a container, and especially a container that can be somewhat agnostic, it doesn't matter whether I'm on RHEL 7 or CentOS 6.5 or Ubuntu 14.01 or CoreOS, because that container, which brings its dependencies for the application, will run in a consistent fashion anywhere that that containerization engine will run. And that's actually, it's not even a function of the containerization engine. Like, Rocket is, and I'm happy that John isn't here because he would, he would shed a single tear. Rocket is a really neat trick, but all of these containerization engines are just using pieces in the Linux kernel. They're using the namespaces that the kernel provides. They're using the C groups that the kernel provides. They're using all of these primitives, and they're packaging them up in an extremely easy to use way. Like, I was talking to a large financial institution back in November of last year when we were first getting ready to release Rocket. And they said, look, any of my guys can write 30 lines of C code and carve out some namespaces. Tell me what's interesting about this. And that really gets to the heart of the point very quickly. All of these things are a function of Linux. And this is an important distinction. Folks like myself and, people who have been into Linux, who do Linux, we laugh about folks like Richard M. Stallman. Bet you didn't think I was going to go there with this. Linux is not an operating system. Linux is a kernel. And then there are packages of things around that make it different distributions. It's the same kernel in RHEL as it is in Ubuntu or CoreOS. They may be different versions of that same kernel, but it's the same kernel. And it's the packaging that goes around that makes it different. It's the fact that Red Hat has built an ecosystem around RPMs, and that the folks at Debian have built an ecosystem around deb files and then made it easier to use through apt that makes that what those are. And it's the same difference of like the difference between a Ford and a Toyota. They both have extremely similarly designed combustion engines. It's just the trim that goes around it. And when you keep in mind that it is just a Linux kernel and then it's the things around it, containerization also makes a lot more sense. Because it's just bringing all the dependencies that singular application needs in such a way where it can consistently run it, regardless of what all of the other trim around it is. The trim is there for the administrator to make things operate in an efficient fashion. Now, I see a question in the back there, so we'll get to you, Kelsey.
Thank you. I'm going to reveal further ignorance. So,
Welcome.
is there something in the the Open Container Format Standards or Docker or Rocket or anything that specifies a required kernel ABI version?
Within both of them, I believe. It's been a while since I've looked at the AppC one, and I'm woefully ignorant on the OCF. But I know that in AppC, there was actually a specification for that, because one of the first things that happened with AppC is that someone wrote an implementation of AppC for FreeBSD, which every single person in the office went, a what? Huh? And it illustrated very, very poignantly that there was a need for actually specifying that. Now, I can tell you that when it comes to the API and the API of the Linux kernel, I've gone back as far as pulling a Cobalt Rack 3, which had an AMD K62 processor in it, and pulled binaries off of that and put them on a Linux system that had multi-lib support, so it could support 32-bit libraries, with a 3.18 kernel, and they ran. Like the Linux kernel itself has done a wonderful job of keeping that contract in place. So I think it's being specified, in the specifications to make sure that that contract has a strong guarantee around it. But I don't know how much the various implementations have really gone full force into ensuring that's the case. Now, knowing that Microsoft is getting involved with the Open Container project, I'm sure that somebody is going to specify that, because you need to be able to say, my kernel is Linux, my kernel is whatever the code name is for Windows, my kernel is Darwin, my kernel is whatever, to make sure that you can navigate that correctly. Any other questions? Okay, yes?
Kind of a simple question around the build root.
Mm-hmm.
So that generates a make file. That's something you can just ship around, right?
Yes, so actually, speaking of that, let me go over here and say gist.github.com/BrianRedbeard. So I actually have a bunch of build root configs. Oh, that's a recipe for tonic syrup. That is this right here is a wonderful auto response that I have to recruiting letters, courtesy of my friend Lee, that calls out asking, like, is your health insurance policies transgender inclusive? How many women engineers do you have at your company, et cetera? But I also have embedded in here, especially on the public side, a bunch of build root configs. And this is the full build root config, but there's also a way of minifying them as well and making them portable across versions of build root. And the way...
It just looks like the old Linux. Okay.
Yes, very, very much. So even when I get down in here, and it's funny that that's still building. It builds everything from scratch. Like, it just drops it in a, oh, you cannot actually see that. Let's fix that. So it drops it in a .config file in your directory. So you don't even have to use make menu config. But I remember my second week of working at CoreOS. I'm sitting down at a table, nervously typing away, and all of a sudden, Greg KH starts shoulder surfing me while I'm compiling a kernel and goes, "Redbeard, what are you doing?" When the maintainer of stable is asking you, "What are you doing?" you immediately freeze up. And I go, "I'm compiling a kernel." He goes, "What are you doing, though? Use menu config. We put all of the effort into building that for a reason. I use make menu config. What's wrong with you?" Learn from those much smarter than all of us. Use those tools. This is great for making like a backup. But they also have a process called make save. Well, so everything is built from this awesome makefile, which Crawford, who was the picture of the dumb developer, is anything but a dumb developer, and he rails against poor makefiles day in and day out. He's a hero of mine. But within this makefile, they have things like make, save, def config. And when you actually run that, it will output a minimal version of your config in, we'll put it right here in def config. And you see that, like, that's just the changes I made. There's literally nothing else. So I can now back that up, and when a new version of buildroot comes along, I can have it generate the full config file from that def config and go to town. On top of that, because this is actually designed to build full Linux distros, you'll notice that there's a directory called configs with all kinds of hardware configurations, including things for your BeagleBone and your Raspberry Pi and your Minoboard Max and everything else. And similarly, there's a board directory with all of those same manufacturers. This is really built to build Linux distros. So you could build an image to be used as a container, as well as building an image to be used inside of, like, your embedded device. Nothing's stopping you. I mean, it doesn't even have to be an embedded device. You could build it for, AMD 64 and go to town. But this is actually how, like, I build my Raspberry Pi images that have systemd in it. Yeah, you heard me. I run systemd on my Raspberry Pis. What? So, but at that point, we're starting to get a little late in here, and we want to make sure that the folks over at Sysdig have time to wow you with their stuff. Because I can say, like, the first time I saw a customer handed me a Sysdig artifact and said, "Oh, can you figure out what's going on with my host?" And I had that, like, mind-blown moment. It was pretty great. So, no more questions. It is now on to the folks over at Sysdig. Thank you very much.
Hello, everyone, and welcome to Sysdig into CoreOS environment. My name is Gianluca. I work as a software engineer at Sysdig. I'm a core developer of the open source troubleshooting tool Sysdig, and obviously I'm a big CoreOS fan. Today we're going to talk about real container visibility use cases applied to CoreOS. This is meant to provide you with immediate value and with nice tricks that you can then cherry pick and use it in your day-to-day adventures in Sysdig. So pay attention. The talk is organized in 3 parts. First, I'm going to present a simple distributed application on CoreOS that I'm going to use for all the use cases. Then I'm going to introduce you to Sysdig, which is the tool that obviously I chose for doing the troubleshooting. And then the most part of the talk will be about real use cases and very cool stuff. So let's start with the demo environment that I'm going to use. This is going to be a simple web application made of a 2-node CoreOS cluster. On the first node, which I will call front end, I have 4 NGINX containers that are just serving static assets, so not much going on. In the second node, I have a balancer that I call balancer host. I have 1 HA proxy container that provides a single entry point inside the application and essentially forwards and distributes all the HTTP requests towards the 4 NGINX container. Then, to add a bit more mess to it, I implemented a simple service discovery using etcd and confd. So what happens is that each NGINX containers, upon starting, will write its IP address into the etcd key value database that is active on CoreOS. And on the other side, I have confd, which is a little application that will periodically poll this set of keys containing all the IP addresses of the NGINX containers and will generate an on-the-fly runtime configuration for HA proxy so that I have essentially, if one container goes down, my application will keep behaving correctly. The infrastructure is bootstrapped using Fleet, obviously, and the container-to-container networking is provided by Flannel. Before jumping to the next step, this is the infrastructure. To prove you that I'm not lying, essentially I have 3 terminals that I'm going to use for the rest of the presentation. The upper ones are on the balancer host, and the lower one is on the front-end host. And here, if I do a fleet control, list machines, obviously I can see that they are in a CoreOS cluster. If I do a list units, I can see, as promised, that there are 4 front-end units and 1 HA proxy unit. So if I do a Docker PS here, I see that there's the HA proxy confd Docker container running. And if I move to the front-end host and I do a Docker PS, I see that I have 4 NGINX Docker containers named from front-end 1 to front-end 4. And we covered this part. As I said, I'm going to use Sysdig for doing all the use cases. So for the poor guys who don't know what Sysdig is this fairly recent open source system troubleshooting tool that works by capturing system events, and I'll define in a second what I exactly mean by that, allows you to filter them and run useful scripts on them. It can be thought as a mix of strace, tcpdump, lsof, htop, so pretty common tools that every sysadmin should already be very familiar with. It's completely open source. It has a nice command line interface and an even nicer cursor-based UI. It has native support for containers, obviously. It's been designed around containers. And the most important for today is very CoreOS friendly. How does Sysdig works? This is your typical architecture of your host when you're running containers. So you have one single instance of the kernel running inside the host, and then you have a bunch of applications. Some applications are outside the container, and other applications are inside the containers for isolation and resource control. But the interesting thing is that each process, regardless of where it's living, inside or outside the container, will interact with the kernel the same way, which is via system calls. So from that point of view, it doesn't matter where the process is living. So by leveraging this fact, essentially, Sysdig works by instrumenting through a little kernel module all the system calls that every process in the system is doing, and it delivers them to the Sysdig user space application that can live outside the container, or even better, inside a separate container. And by using this approach, which is, again, very useful, especially in situations like CoreOS, where you have a very minimal host distribution, and everything that you need to do it in a container. Sysdig is able, by sitting on a separate container, to see what's going on in all the system and for all the processes. And yeah, as you'll see, this will provide you with immediate value and very, very interesting use cases. How can one deploy essentially Sysdig? And I'm essentially going to just refer to CoreOS, since this is what we are talking about today. On CoreOS, there are two ways on which you can deploy Sysdig. One is by using our official Docker image that we provide and maintain and contain some eye candy such as bash completion and stuff like that. But we know that a lot of people like to use the toolbox, so you can just install Sysdig using apt-get or yum, and it will just install the Debian or RPM package depending on what base image you're using for your toolbox. And after this introduction, let's jump into finally the interesting part of the talk. And these are the use cases I'm going to cover today. And I'm going to start with a generic system exploration. So just explore our demo infrastructure to see if there's something going on. Let's get rid of these slides finally. And I'm going to focus on the balancer host. So here I'm going to run the Sysdig Docker container with the command line that we have just seen in the slides. And once I run it, essentially, I'll spend 1 minute, not more, talking about generic Sysdig, and then we'll jump into more interesting stuff. Sysdig in its simplest form, again, is a binary that I can run, and if I run it like this, it will essentially print me on screen all the system events done by all the processes in the system. So, oops, okay, I got a little bit of a lag. Yes. So it will print me on screen all the system events done by all the processes in the system. And again, this is very verbose, noisy, and not very helpful. So if you remember, the second bullet point of my slide was you can capture system events, but you can filter them. So for example, if I use Sysdig -L, I have access to all sorts of these stateful filters so that I can filter by specific file names, by specific connections, by specific process attributes, and containers, obviously. So for example, I can do this command line, and I can run Sysdig, and I can use as a filter container.name equal haproxy confd. And now I get a much better output immediately. In fact, I see a much more limited set of events. And I just see the events, not surprisingly, from the haproxy container, along with the container ID, and the container name and the container ID, and all these events. So depending on what you're looking for, this is much more useful than the previous thing. But where Sysdig really shines is with chisels. With chisels are some simple scripts that you can choose to use instead of this flat list of output. And they work this way. Essentially, they will process the events for you, and they will just print you on screen what you're really interested in. So for example, if I do -c, I can see here the few dozens that we ship by default with Sysdig. And let's use an interesting one, for example, top files bytes. And here I immediately get something more interesting. Now I'm not getting the flat list of events, but I'm getting the IO file activity done by all the processes in the system, broken down by container and by file name. This is an incredibly useful metric to have, and there are not many tools around that can do something like this. You can use IO top or stuff, but this that breaks down the IO by file name and by container is pretty useful. And we have tons of chisels like those. We call them chisels. They're written in Lua from an open API that everyone can use, and it's very easy to improve and extend. Then, as I said, this was the Sysdig, so the command line tool, but then we have what we call Sysdig, which is our cursors-based UI, which, if you take a look at it, it will remind a little bit of htop. We ripped off the color scheme. But if you see here, you will immediately see one very interesting column, which is the container. So Sysdig will immediately tell me the container name on which the processes are living, and I can filter on them. So I can put haproxy to just see them. So again, this is something very useful. And the similarities with htop essentially end here, because we have this pretty neat thing called the view panel that one can use by pressing F2. And this will show me all the views that we support based on those system events. So at this time, I was looking just at processes, but I can, for example, look at containers. And now I get an overview of all the containers in my system, along with the network activity that they are doing, the file I/O that they are doing. So this is a very good for a top-down approach where you are just doing generic system exploration, is updated in real time. And say that I want to see this HA proxy confd container. By pressing enter, we do what we call drill down, and I brought to the view that just shows me the processes that the HA proxy container is running, which in this case is HA proxy itself, and then confd, as I said, which takes care of the service discovery. But once I'm inside a container, I can, of course, browse the views panel. And for example, I can look at connections. This is something that is also very unique to have. Now I'm just getting the network connections done by these containers that I was in. And in fact, I see that these are all connections towards port 80. So it's HA proxy probably doing some sort of health check towards the 4 NGINX container on the remote host. And the views are super cool to explore. For example, one that I like a lot is file open list. That will show me the list of open files by each container in real time. So in this container, I have confd, which is opening the HA proxy configuration file every 10 seconds to refresh it by fetching information from etcd. And in fact, I can see that it's completely precise because at 42 it started and then at 52 again. And I can see that it's messing with the HA proxy.config configuration file. And again, all these views are nice to explore. Too bad we don't have enough time. So this essentially covers the first system exploration part. So let's jump into something a bit more advanced, which is transaction monitoring. As I said, this is a very simple web application. So I can do a curl here, and I can see that the HTTP request goes through one of the NGINX container and is served. But what is nice when you have the distributed microservices-based infrastructures sometimes is following the path of a transaction from end to end across all your components of the system. And this is something that at Sysdig we thought a lot about. And in fact, I can use a chisel that I'm going to call, it's called the echo file descriptor chisel, that will print me on screen all the I/O buffers exchanged by all the processes in the system. So these are very verbose output, but if I combine it with a filter such as process name equal HA proxy, and now I run my curl command, I immediately see a very cool output that contains all the I/O buffers, the exchanges that HA proxy did for serving this transaction. And in fact, I can see that HA proxy on the HA proxy confd container on a connection from localhost to localhost, which is the one coming from my curl, read this HTTP request. And then it immediately forwarded it to one of the to one of the front-end containers, 5.4, so it's probably NGINX 4. And it forwarded the same HTTP request by appending the X-forwarded for, obviously, HTTP header. And once this is done, then it reads from the same remote connection, it reads the HTTP response, which contains, of course, the HTTP headers and the body, as expected. And then it forwards it to the localhost to localhost connection where curl was waiting. So again, this is simple, but you are not always that lucky, and sometimes, especially when there's more stuff involved in a transaction, this can pinpoint some pretty nasty things. Same thing if I want to see how my transaction ends into the front-end containers. I can go into the front-end host, and I can run sysdig just as before here. And I can use a similar command line. I'm going to use sysdig container.name contains frontend. Notice the fuzzy matching, because I don't know which one of the NGINX container will serve my transaction. So with this, I can catch them all. And if I do a curl, oops, of course, I forgot to put the chisel name, echo file descriptor chisel. And if I do it again, now I get essentially the respective part that I can see that the request was served by frontend 4, I can see the HTTP request, the HTTP response, and I can even see that Nginx at some points writes essentially in the log file the entry for the HTTP request that is served. So this provides you a very good global visibility of everything that's going on, that is going on. And again, this is a use case that I use all the time because transaction following and monitoring at this level, it's simply amazing. Let's move on to something more complicated, which is confd troubleshooting. So as I said, I'm using service discovery, and I introduced a bug in the service discovery. And we're going to use Sysdig to trace it in a completely passive way. So let me just set this up by running a poor man's version of a traffic generator where I essentially run my curl in a while true bash loop so that I keep my infrastructure going. And let's go to the front-end container, to the front-end host, and let's run Sysdig. Now, this is too much, I don't care. I want to go to the containers view. I want to sort by name, and who can see what's wrong here? Essentially, I can see that all the front-end containers are here. They are all doing network activity except front-end 2. Look here, it's doing zero. It's doing zero network activity. So there is clearly some problem either on this side or on the other side of HA proxy. How can I find out? Well, let's zoom in into the front-end 2 container. First thing I see, Nginx processes are up and running. I have the master and I have the worker, so everything is fine so far. Let's look at the network connections. There doesn't seem to be any network connections, so HA proxy is not even trying to talk to Nginx, otherwise I will see them here. Let's go back to the processes, and to confirm that Nginx is completely idle, let's do what we call the dig into. So by pressing F6, I'm brought down to the Sysdig event, to the flat list of Sysdig event, just for this Nginx container. And here I can see that essentially Nginx is not doing anything. There's just this proc info meta event, which is just some internal stuff that Sysdig uses. So Nginx is completely idle. So at this point, I'm starting to think essentially that the misconfiguration is on the HA proxy side and confd. And in fact, let's move to the tier. Let's move back to the balancer container. And let's do the same. Let's run Sysdig. And let's jump straight into the HA proxy confd container. Now, as I said before, the confd works by polling every 10 seconds the set of keys from etcd and regenerating the HA proxy configuration file. So I kind of want to see what is confd doing from a IO buffers point of view. So once I select the confd node, I can press F5 and I can enter into the echo file descriptor mode right from Sysdig, where I will see the periodic activity that confd is doing every 10 seconds, which happened just now. And once it's done, I can pause it, and let's analyze this. The first thing that confd is doing is talking to etcd. You can see on port 2379, it's asking via simple HTTP request this key, HA proxy discover services, which is the one that I used for the in the Nginx containers. And I can see here the response that is a JSON and contains, it's supposed to contain all the IP addresses for all the front-end containers. In fact, if I start looking here, let's see, where are they? I can see that I have the, here, front-end 1, perfect. I have the front-end 1, and I have the IP address and the port correctly set into etcd. And then I have, if I move on, I have the front-end 2, but from the front-end 2, I don't have anything. I just have port 80. So it means that for some reason, the IP address of the front-end 2 container didn't end up in etcd. So this might as well be the cause of my problem. Just to further check, I have front-end 3 here with this endpoint correctly set, and front-end 4, same. So it's just front-end 2 that is missing the IP address. Let's see how confd behaves. So right after getting essentially this JSON object containing the front-end endpoints, confd starts reading the haproxy.temple file, which is the haproxy configuration file in the confd templating language, which contains some boilerplate, and then it gets to the interesting part. If you've ever done haproxy configuration, you'll recognize this backend statement. And this is essentially supposed to be a loop where you put all your endpoints, right? So this template will be processed at runtime by etcd, and the final static configuration will be written, which is what happens here. We can see that immediately after reading the template, confd starts writing to this haproxy.config with some random ID, and starts writing the template file as it is evaluating it. In fact, we can see here the boilerplate, which was all static crap, and then it starts writing in chunk all the evaluation of the template. So if we iterate over here, at some point we'll find the backend keyword, which is right here. And from this moment on, the front-end endpoints are being written. I can see front-end 1 with the right IP address, and front-end 2 without anything. So this clearly pinpoints the bug. In fact, I can see that after the template is being evaluated, the final file is being actually read, which contains in clear text what's actually going on. Front-end 2 doesn't have an address, so no wonder my front-end 2 container was inactive and idle. This turned out to be a bug in my fleet unit file. So if I stop my traffic generator and I show you the unit file, essentially here I was doing some very messy things, and I was running my nginx container as a fleet unit file, and then I was using as a trigger for the exec start post, I was using etcd control to set the IP address of the front-end container inside etcd by using the docker inspect. But it turns out that by the time this trigger is executed, sometimes Docker still didn't fully initialize the container, so this was empty. And again, this was slightly more complicated, but it's something that can definitely happen in reality. And I want to stress on something. This was completely troubleshooted by doing passive things. I didn't do any Docker exec. I didn't need any, as Brian was saying, didn't do any text editor inside the container, because containers should be extremely lightweight. And just by passively seeing what was going on, I was able to clearly identify the cause. And this is even more important in production, where even if you have your VI inside the Docker container, you don't want to connect to them. It's just bad. And yeah, so this was a more interesting use case. Now, simpler one before jumping to the big one. This one will be monitoring container bootstrapping. So one thing that I have always been annoyed by was how the Docker entry points are big and messy. And especially when you're building your own container, troubleshooting them is a pain in the ass. You need to put tons of echoes in the entry point script and stuff. So with Sysdig, we came up with this Sysdig mode that we call spy users, that will show you all the commands executed in the system by any process or container. So if I do, for example, I temporarily stop the haproxy unit file, I can see that here I get fleet control stop, and then I get docker stop, not too much exciting stuff. But if I start it again with start, now I will see not only the fleet control, but also my Docker entry point as it's being executed. I can see entry point.sh, followed by confd, which is running one-shot mode, and followed by haproxy, and then the final confd run. Again, this entry point, I was extremely lucky, but I could point you some public Docker images where you get hundreds of these commands being run as an entry point. And it's like I've done it very recently for Cassandra to debug a bug in their Docker image, and it was quite effective, especially if combined with the previous view that will show you the flat list of events, because then you can see, for example, the return codes of each process or the files that it accessed. So very powerful. Again, this was short, and let's jump into the last one, which is the most advanced one. It will be about flannel troubleshooting. So if you've seen here at the first echo file descriptor, when I was doing the transaction monitoring, there's something quite interesting to notice. Here, HA proxy directly talk to the IP address of the dock or the front-end container sitting on a remote host. This should not be possible because by default, when you run Docker on a host, it creates a private network, and each Docker container gets a private IP address from that Docker network, and that network is limited within the host. So if you have two containers on separate hosts, they cannot communicate with each other unless you do port forwarding, which is not the case because I can see that it's communicating on port 80, and all four were listening on port 80. So this is clear not port forwarding. This essentially is made possible by Flannel, which is an application that the CoreOS guys did, that essentially works by creating a virtual network that spans across whole your cluster, and every Docker container will get an IP address of from this global virtual network, and so that one container will be able to talk directly with a remote container, even if they are not on the same host. And Flannel, when this happens, will take care of taking the network packets from one container, encapsulating them over a tunnel, which can be implemented in various ways, but by default is done by a UDP tunnel, encapsulating them on a UDP tunnel where they go through a physical routable network. And once they reach the destination host where the container that I want to talk to is, then Flannel will take care of injecting the packet into the network of the Docker container. So it is quite advanced, but I find it very cool to troubleshoot this with Sysdig and see what actually means from the point of view of the system, all what I've talked about. So for this, I'm quickly going to introduce you to a new mode of Sysdig. If I run sysdig-w trace.scap, now I'm not viewing on screen the system events, but I'm saving them on a trace file, which is something that we borrow from the workflow of TCP dump and Wireshark. And so if I now do a curl, I don't get anything on standard output, but I get a very useful trace file that I can analyze offline as much as I want, and I get the same level of visibility that I was getting live. So by running the echo file descriptor on the trace file, I'm able to completely reconstruct the transaction. And again, this is a super powerful workflow, which in fact I'm going to use to troubleshoot Flannel. What I'm going to do for Flannel is this. I'm not going to use any chisel, so we're going to get hardcore on the system events. And I'm going to use as a filter for HA proxy or flannel-d, which is the daemon, flannel-d. So we'll get all the interactions between HA proxy and flannel-d. And once I run this, I get a whole lot of system events, and hopefully we'll make some clarity out of it. So let's start by looking at the entry point of this thing, which was the moment where HA proxy received the HTTP request from curl. So I'm using just my terminal, and I'm looking for the get slash, the entry point, and I get it here. So at some point, HA proxy received from a localhost to localhost connection this payload, which was the HTTP request. I'm using on the left the hexadecimal output because we will use it in a second, and it's quite useful. So as soon as HA proxy receives the HTTP request, it will essentially try to forward it to one of the Nginx containers. So in fact, I can see here that HA proxy tries to open a connection with the connect towards 192.168.5.4, which is probably the front-end 4 container. And this connection returns E in progress, which means that it was open in asynchronous mode. So from this moment on, HA proxy will just block and will periodically wait until the connection will be declared as open. In fact, we can see that here we'll start doing a bunch of these epoll wait, which is the system call that you use for polling for asynchronous event at the system call level. And while HA proxy is waiting for the connection to succeed, we have on the other side Flannel doing all the magic. So Flannel will recognize that HA proxy is trying to talk to a remote container and will start forwarding on this tunnel, which notice is a UDP connection because it has this 4U, that in the Sysdig terminology means IPv4 UDP stream, and will forward it to 10.1.1.116, which is the physical address of the host where the front-end containers are living. We'll start forwarding this blob. And this blob, if you've ever done networking, this is just a TCP packet. So flannel is essentially simulating the instantiation of a TCP connection over the UDP tunnel. In fact, if I select this and I just for 1 second go here and I just select the byte stream, then I'm going to go online. There's this nice Wireshark hexadecimal tool that I use that will essentially decode me the IP packet. I can see that this is an IP packet directed towards 192.168.5.4, is a TCP packet on port 80, and it has the flag SYN. So this is the first part of the TCP three-way handshake, which are the 3 required packets that needs to happen for a TCP connection to go through. And in fact, I can see how flannel is forwarding this stuff. And it read the same thing from the virtual network file that the Linux kernel provides when you create a tunnel, which is the facility that flannel is using. So this is the first part of the TCP three-way handshake. Then I have that flannel goes with the second part. So I can see that the second part, the SYNAC, comes from the other host. In fact, it is received from the tunnel. This byte stream is received from the tunnel and is forwarded to the container by writing into dev-net-tune interface. And this was the second part. And then I have the third part, which are these last 2, which go into the opposite direction. They are read from the container and they are forwarded to the UDP tunnel. So after this, the TCP three-way handshake is completed and the HA proxy can finally be unlocked. In fact, I can see that right after, the call to HA proxy to Apple wait will return 1, which says, hey, you have 1 socket that has finally activity. And right after doing this, HA proxy, not surprisingly, starts forwarding to the private IP address of the front-end 4 container, starts forwarding the HTTP request. And which then again, as you now know better than me, is then read by flannel from the tunneling interface and forwarded to on the UDP tunnel by prepending a bunch of crap that we can see now once again on the editor. Here, let me do a vertical selection. Yes, let's put it here. So if I do this, not surprising, is an IP packet on port on port 80 towards the front-end 4 container, but this has an HTTP payload, so it's also layer 7 network packet, and it contains the get slash. So this was the HTTP request. So this was a bit advanced, and maybe most people will not need this on their day-to-day troubleshooting, but I find it quite fascinating because I always wonder, how do these things happen from a technical point of view? It's cool when you say, yeah, it's a virtual network, blah, blah, blah. But when you see how things happen from a practical point of view, it's quite interesting, at least for me. Yeah, so this concludes all the use cases. I just have a couple minutes, one more bonus item. So as you've seen here, I am using pretty hardcore tools on a specific set of hosts. But sometimes, especially when you're in production, you have dozens, if not hundreds of thousands of hosts. So this is not a scalable approach, right? You cannot, oh yeah, let me run Sysdig and spend 10 minutes on each server and see if there's something wrong going on. So what we did was essentially writing Sysdig Cloud, which is our software as a service and on-premise infrastructure monitoring and troubleshooting tool that essentially works by collecting all this data that comes from Sysdig from multiple hosts. And it works essentially by presenting you all the information about your infrastructure in a very convenient place and centralized place. So here I can see that I have a bunch of hosts that are grouped by arbitrary tags, and I can expand each group and get to access to the hosts, and I can expand each host and get access to the container, along with a bunch of useful metrics that I can sort on, or that I can look their values arbitrarily in the past to see if there's something that was going wrong while I was sleeping or hanging out. And once I see that there's something wrong, I can, for example, click on one container and I can get access to hundreds of more metrics, and even interesting ones such as HTTP, where I can see the HTTP transactions that were done by essentially my container. All this by passively monitoring on a separate containers, all the other containers are processed in the system. And we have tons of these views, and we also have something more, let's say, fascinating, like this map that our users like a lot, where I can essentially see a topological view of the same resources that was seen before in the table. So here I can see how they talk to each other in terms of groups. And if I'm not happy with this view, I can expand each group and get access to the hosts that are composing the group, which are the same that I was seeing there in the Explorer, along with their network connections and how they are communicating with each other. And if I'm not happy, and I'm very picky, I can expand one host and get a visibility into the containers. So, nice. I can expand and see all the containers. You'll notice that this is a quite similar infrastructure to the one that I just demoed you, but it's just on a single host. And I can see HA proxy talking to a bunch of WordPress containers with network connections. And if I'm not happy, I can expand to one WordPress to one container, and I see now the processes, how they are talking to each other. And okay, now I'm happy. And the quite interesting thing is that all this information has been drawn from the very boring flat list of system events that you saw at the very beginning of the presentation. You said, what the hell am I using this for? Just by processing all this chunk of big data, you're able to do some pretty cool stuff and pretty cool applications. So yeah, I think the bonus item is over, and I'm done. If there are any questions, I guess can take. Okay.
What's the performance impact? You said it's passive monitoring, but doesn't it use system traces?
Yes. So you can essentially divide the overhead in two parts. There's the kernel overhead part, which is the overhead that you need to capture the system calls, and that is very minimal. We are talking about, like, for normal use cases, unless you are really bad and really want to stress in some way, for example, by doing a very anomalous number of system calls compared to the other activity, they can become significant, but otherwise it's safe to say close to zero. And then you have the cost on the Sysdig point of view from the user space level to parse, and that depends on what you do. Like if I'm saving a trace file enabling compression with Z9, it's going to get to a bunch of CPU. If I'm just running a lightweight chisel, it's going to be very low. Yeah, and for the Sysdig Cloud, we just use recompiled version of Sysdig, which is more optimized for this thing, and that's supposed to be low overhead 24/7 always. Yeah.
As much as I like Lua, not everybody does. So do you guys have any plans to allow writing chisels in other languages?
So for the time being, we just have Lua, but there are essentially two options that one could use. One is directly interact with the Sysdig binary that we have that supports JSON output. So you can configure it to say, hey, export me this field, this field, this field, this field in JSON. So we had people like writing a plugin to push the JSON to Elasticsearch, for example. Or even better, if you go on our GitHub, you will see that Sysdig is decomposed in system libraries, and we have this libsynsp that is called libsystem inspector, and that is as essentially a C++ API where you can essentially do everything that you would like. So if one will want to write a hook for calling a Python script or even do some processing in C++, they could write their own client without even considering Sysdig, just by using the system instrumentation stack that we provide. And Sysdig, the two applications that you have seen, Sysdig and Sysdig, are a very thin layer on top of the whole instrumentation stack that we have. So you can, by doing, there are DLL that you can compile, shared objects. Shared objects that you can compile, you can do pretty much everything you want, yeah.
Yeah, what is the latency between the ring buffer and the chisels running? Like, if you were to use this for intrusion detection, you want to capture a process that runs and it goes away real quick.
Yeah, so we are really talking about very, very little. Like the thing we are doing some polling of the ring buffer, we are talking about, in the worst case, it's about 30 milliseconds. Like the very worst case, usually is much more, usually the application, if the system is not busy enough, and so the context switches are polite towards the Sysdig process, we are talking about in hundreds of microseconds, you'll get the event. Yeah. In fact, we have some, if you go on our blog, we have some very nice security and IDS-like use cases for Sysdig, which, yeah.
Okay, great. Thank you.
A fantastic presentation, by the way.
Thanks.
So following up on this gentleman's question, the resolution of in-kernel objects to like full commands, paths, things like that, is that asynchronously done then after?
So yeah, essentially what happens is that in kernel mode, we do as little as possible. So in kernel mode and in line with your application, we just capture the system call and the system call parameter, and we flush them into a ring buffer, which is then read asynchronously by the Sysdig application. So if the Sysdig application gets stuck or it's slow or there are too many events, the ring buffer will just fill and all the events will be dropped. But it has been designed to be one, extremely simple in kernel mode because we are not good programmers. And the second thing is it has been designed to have very little overhead with your application, which is what you should care about. Yeah.
Can you tell us more about Sysdig Cloud? You know, how much did you say?
Beautiful thing.
All right. Is it open source? Should we figure out, you know, if we have a CoreOS cluster of, 20 hosts and, say 100 containers, and, how do we look for sizing, disk space requirements if you want to capture logs, or Sysdig events, for 2 weeks,
Yeah.
blah, 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 blah.
So-
How would you start to approach
Yes,
Yes,
definitely. So Sysdig Cloud is not open source. At this moment, it's closed source, but the instrumentation part, which is what is critical, is open source. It is essentially we use the same kernel driver, which was, a good move on our side because we got tons of testing from the community and stuff, and 90% of even the agent, which is the part that reports, is open source and part of Sysdig. Sysdig Cloud is not open source. It works by having a software as a service or an on-premise version. So if you use the software as a service, you just essentially pay us and you can do whatever you want. You can deploy to your CoreOS stuff and you're good to go. You can infinitely scale almost. And if you install the on-prem version, essentially it's up to you. We have some sizing guidelines. So at this moment, as you can imagine, this is pretty rich information because I just showed you not some super crazy stuff, but as I was saying, we have, for example, now the connection is a bit lagging, but I have, for example, top files being accessed in, here I have the connection. So yeah, I have top files being accessed in real time for an arbitrary time of data that I can jump back. So this is rich data. So we provide a sizing guide. As a general rule of thumb, each node with moderate activity will generate about 1 gigabyte of storage or something to store all this data. And there's of course rolling up processes that will essentially make the data more coarser as you approach, as you go farther in the past. Yeah. No. We're really talking about month or years. Like what happens, for example, we keep the 1 second granularity for 6 hours, then we keep the 1 minute granularity for 2 days, then we go to the 10 minutes granularity for 2 weeks, 1 hour for 3 months, 1 day for unlimited. Thank you. Yes, thanks.
So my original question was, your environment had the 4 Nginxs on one machine. My question was going to be what if they're on 4 separate physical machines, but this cloud thing seems to pick that up. But I'm still wondering, can you point the CLI at the cloud? Because I'd rather use that, for automating things or digging into things myself.
So your question was if you can open the Sysdig CLI from the cloud application?
Can I
or-
point it at the, instead of like a trace file, can I point it at the?
Oh yeah, so essentially we can integrate in a bunch of ways. So at this moment you essentially have two options. Once you see that one host is misbehaving or something, you can SSH into it either from your machine or
I
here.
don't know which machine it is, right?
Yeah,
Your
no, no.
example, you were tracing the 4 Nginx's on one physical machine.
Yeah.
Right? What if those containers were on 4 separate machines?
Yeah,
You have to open 4
so
windows and trace them?
once here, for example, I'm going here in the map, and so here, for example, we are seeing the
Yeah,
CPU.
I get it from here, but if I want to do that from the command line, if I want to trace across physical hosts.
Oh,
containers-
no, okay, yeah, sorry. No, the command line so far is designed to work on a single host. Yeah.
I get that. You were pointing it at trace files. I was wondering if you had plans to point it at your cloud service.
Yeah. At the moment we don't have that. Yeah, but it's definitely an interesting use case. Yeah, yeah. But there are several ways through which we kind of integrate. For example, you can take a Sysdig trace file right from here that you can then analyze on your laptop. Yeah. I completely understand your point. No problem. Okay, thanks everyone.